Okay, so let's finish the ultimate Picard little theorem. Okay. The theorem says a non-constant higher function assumes every value in the complex plane C with at most one exception. So it's a very strong view. Okay, so let's take the proof. Okay. Okay, so okay, so the thing is that we may assume the function ft that so if the function ft obeys two values, then we can assume it to be the function. Yeah. So basically, what we can do is that we can assume the point. So if we have a function that means like 2 points, right? So then what we can say is that we can let the function. Okay, so okay, so that's the proof. Okay, so okay, so okay, so suppose okay, so that's that on this. Okay, so that on this. The value A and B. Okay, so let's assume we have these. Okay, so then we can define the function g to be so then we let g z to be defined as is fz minus what do I want to say? so okay, this is one thing. Okay, so we'll let G to be that. Okay, let's see. So since fz of this value a and b, right? So basically, fz cannot take the value a, right? Which let's see, which yeah, fz cannot take value a, which gives you 1, right? And can there be another value that gives you 1? No. Okay, there's no other value that gives you 1. So yeah, so that's the only value that gives you 1. Okay, so then fz cannot assume value b. Okay, so okay, so where a, b, of course they are different. Okay, so yeah, so okay, so can G assume value? So okay, fz cannot assume value b, right? So yeah, right. So then that's the only value that gives you 0, right? Okay. Okay. So wait. Okay. So yeah. So then we have GZ. The GZ omits the value uh, 0 and 1. Okay. So now, okay. So now by the okay, so therefore by the Scotty theorem, so we have this so because so remember that the condition for Scotty theorem is or wait. Okay, so let me recall. Sorry, let me check. Yeah. Okay. So the condition for Scotty theorem is okay. So okay. So this GZ, of course, it is because okay, because this fz is like an entire function, right? So and then these are all constant. So therefore, this GZ is also entire, right? Okay, and of course, GZ is entire, and then okay, GZ is entire, and then GZ does not assume. Yeah, GZ is entire, and then it does not assumes either 0 or 1. Okay, so therefore we have that for any theta, right? So there is a constant that depends on this G at 0 and then theta, right? So where this theta you can imagine is like a number from 0 to 1, right? So 0 less than equal to theta less than 1. Okay. Wait, theta? Okay. All right. So okay. So by Scotty theorem we have so remember this. So okay. So the thing is that okay. So let's just state the Scotty theorem. So the Scotty theorem is modulus of GZ is less than this constant of which depends on the G0 1 half. Okay. So for all right. So yeah, because GZ is analytic in any disk of radius r. Right. Okay. All right. So okay. So the thing is that here, because again, as I said, this r could be arbitrary, right? So okay. So now the thing is that then since okay, so here since so r can be arbitrary. So therefore we have that this GZ has a this GZ is has an upper bound. Okay. Therefore, Hughes theorem implies that wait, yeah, Hughes yeah, Hughes implies yeah, G is a constant. So again, for the Scottish theorem, I think this this constant is so this constant so for the Scottish theorem, right? So this constant is only depending only on theta, okay, and f there, not on the radius r or otherwise on empty. So yeah. Okay, so I think that's true because this g is constant. Then this implies that this f is a constant, okay, because it's constant times Okay, so I think that's completely proof. Okay. All right. So so I think that's the end of this lecture series, and then I will do another lecture series about the holomorphic universal holomorphic. Okay. About the it's about the universal holomorphic about the holomorphic Coriolis space of C, about this C, because you know that this because this kind of give you a very clear picture on what's the image of the entire function looks like, right? So basically, this theorem just tells you that for any entire function, the image can either be the entire C or just C minus y. Okay. So if it is the entire C, then you just C, right? But the thing is that if it is if the function image is like C minus y, right? So but basically what we can do is that we know that it is we can say something more about this one. Okay. So so we'll talk about it next. Okay. So basically that's about the it's about the okay. About the we'll talk about that. Okay, we'll talk about that.